Good day, students. Welcome to math.serve.com. In this clip, we're going to be going over how to solve functions and also how to find the domain. All right, let's take a look at the first set of problems. Instructions are to find the values that makes the equation f of x equals 0 true. So for problem 1, let's say we have the function f of x equals 4 minus 7x. So the question here is, what x value will make this function equal 0 true? Okay, so all we are simply going to do is we're going to set f of x equal to 0 and solve. All right, we're going to solve for x. So let's go ahead and do that. We're going to take 4 minus 7x is equal to f of x, right? So we're going to set f of x equal to 0. Just put it on the right side using the reflexive property of equality. Okay, so now let's get x by itself here. To accomplish that, we just subtract 4 divided by -7, and we'll be done. All right. So subtract 4, you have -7x equals -4, and then divide both sides by -7, and your final answer will be x equals. Remember, minus over minus is plus, right? So x is equal to +4/7. This is the x value that will make f of x equals 0 true when f of x is 4 minus 7x. All right, let's take a look at question 2. Now, what if we have the function f of x equals 3x minus 3 over 4. Instructions are still the same. What values of x will make f of x equals true? So we're going to follow the same steps. We're going to set the function equal to 0 and solve. Okay, we're going to be solving for x. That's the independent variable in this function. So let's go ahead and do that. Set the function 3x minus 3 over 4. Set it equal to 0. Now we're going to proceed to get x by itself. We need to get rid of this denominator here, this 4, and then -3, and then this 3 has been multiplied by x. So to get rid of this 4, we'll multiply both sides by 4. Okay, and that divides out on the left side. We are left with 3x minus 3 equals 0 times 4, which is 0. Then we add 3 to both sides. We have 3x equals 3. Divide both sides by 3. And then that gives us our final answer, which is x equals 1. Okay, so this is the x value that will make the function equal 0 true. Okay, let's take a look at question 3. For question 3, we have a different set of instructions. Here we have to find the x values that makes the equation f of x equals g of x true. So we're going to be given two functions and find the x value that makes the two functions equal. So for 3, let's say we have f of x equals 12x minus, say 12x plus 32, and g of x equals x squared. All right, well, quick correction. Let's make it 12x minus 32. All right, so make this negative 12x minus 32. Okay, so in order to find the x values that makes these two functions equal to each other, we're going to set f of x equal to g of x, and then we're going to proceed to solve. Okay, we'll solve for x. So that's the set of instructions that we're going to follow to solve this problem. Okay, so let's set the two equations, two functions equal to each other. So we have 12x minus 32 equals x squared. Now, this is a quadratic equation, and when you're solving quadratic equations, depending on the method you're using, I want to use factorization here. You want to make sure that the quadratic is in standard form, basically in the form ax squared plus bx plus c equals 0. So let's go ahead and put this in standard form. Just subtract 12x and add 32 to both sides, subtract 12x, add 32 to both sides. So we have the standard form x squared minus 12x plus 32 equals 0. Okay. Now there are different ways you can solve a quadratic equation. We're going to use the factorization method here. Let's hope that this quadratic is factorable. All right. This is known as the AC method or the X game. We're going to put AC on the top, B on the bottom. AC is 32, and B is negative 12. So we'll ask ourselves a question. The product of what two numbers yield 32 and add to give you negative 12. Okay, so let's go ahead and make our product chart here just to exhaust the combinations and see which one gives us our desired combination. So we have 32. 1 times 32 gives us 32, but when I combine this by addition and subtraction, I get 31 or 33. That doesn't work. How about 2 and 2 goes in 3, 16. This gives us either 18 or 14. What we want is 12. Okay, so that doesn't work either. 4 times 8 is 32. If we add these two, voila, this is the combination that we like, okay, because it gives us 12. All right, so let's put that back in. 4 and 8. Now, we have to combine this in such a way that we get negative 12 as a sum and positive 32 as the product. Now, since the two addends are smaller than this number and the sum is negative, that means both of these two numbers must be negative. Okay? Now, since A is equal to 1 in this problem, that means that we can skip the factoring by grouping component and jump directly to the factored state, which is x minus 4 times x minus 8 equals 0. Had it been A or something else other than 1, then we have to factor by grouping, break this into 4 terms, divide by 2, divide it into 2 parts, and factor by grouping. Okay, but whenever A is 1, then all those steps are not necessary. All right, so using the zero product property, we'll set both factors equal to 0. And then we're going to solve for x, okay? On the left side, just add 4 to both sides, and then your final result is x equals 4. Then on the right side, you just add 8 to both sides, and your final answer is equal to 8, okay? So the x values that satisfy f of x equals g of x is x equals 4 and 8. Those are the two values that we are looking for. All right, so the instructions for the next set of problems are for us to find the domain. Okay, so basically the restrictions on the acceptable inputs of the function in order to get a defined output. Okay, before we get started, let's go over the rules that are going to be guiding our problem solving process. There are 3 rules that we'll be looking at here. Rule number 1, if the denominator is a variable polynomial, basically a polynomial with variable terms associated with it. So if it is a variable polynomial, in that case, what you do is you set the denominator. That variable polynomial denominator, is set it to not equal to 0 and solve. All right. Case number 2, what if you have a radical? If you have a radical with an even index, and a variable radicand. So there are 2 conditions here to find the domain. Not just any radical. You need a radical with even index, like square root has an index of 2, or the 4th root has an index of 4, or the 6th root has an index of 6. Okay? And the radicand has to have a variable component to it. So if you have those two conditions, in that case, you set the radicand to greater than or equal to 0 and solve. Okay, or else you're going to get imaginary numbers. Number 3, a combination of 1 and 2. 1 and 2 combined. Well, what does that look like? You have a radical. I have a radical denominator. Okay, so you have a denominator polynomial, and that polynomial is a radical, but you have to make sure that you have a radical denominator with variable radicand. So the radicand of the radical in the denominator should have a variable. Okay, variable radicand. In that case, what we're going to do is a union of 1 and 2. Okay, so what happens when you unite not equal to and greater than or equal to? So not equal to 0 and greater than 0. When you combine these together, you end up with simply greater than 0. This not equal to eliminates this equal to component of the greater than or equal to. All right. So the instructions or the approach for step 3 is a combination of 1 and 2. So in this case, what you do is you set the radicand to greater than 0. All right, combination of these two and solve. So that's how you deal with radical denominators where the radicand has a non-zero degree. Okay. All right, so with those rules in mind, let's go ahead and take a look at problem number 4. So for 4, let's say we have the polynomial function f of x equals 2 minus 3x squared plus square root of 5. Okay. Now, we don't have any denominator polynomial here, so that's good. We can apply case 1. Case 2, radical. We have a radical here, but the radicand is a constant. So neither of these cases apply. What does that mean? It means that there are no constraints on the domain. All right? Any real number is acceptable. So let's go ahead and write it down. The domain can be written in different ways. You can just put an R there, or you can say all real numbers, or you can write it in interval notation. Just go from negative infinity to infinity is your domain. Okay, so that's that. Let's take a look at problem number 5. For problem 5, let's say we have a function f of x equals 5 over 1 minus x squared. Okay, so let's go back to the rules. Which of these apply here to question number 5? 1, 2, or 3? We're going to use number 1 because we have a denominator that's a polynomial with a variable, namely x squared. Okay, so the rule is we have a polynomial denominator is a variable polynomial. So what we'll simply do is we're going to set the denominator to not equal to 0 and solve. Now this is the reason why. If a denominator is 0, if the denominator polynomial attains a value of 0, then the output will be undefined because you cannot divide by 0. So the goal here is to exclude that value that causes the denominator function as a whole to attain a value of 0. All right, so let's extract the denominator polynomial, which is 1 minus x squared. Set that 2 cannot be 0 and solve. All right, so what can we do here? Subtract 1 from both sides. That yields negative x squared equals negative 1. Divide both sides by negative 1. And then you have x squared equals 1. And then to get 1 by itself, to get x by itself, you take the square root of both sides. Now, since you're taking the square root of a square, you're going to have to introduce absolute value, or you can just say x equals plus or minus 1. Okay, so these are the constraints on my domain. So let's write down what the domain is. Oh, wait, cannot be. X cannot be 1 or -1. All right, domain. What's the domain? You can, in verbal form, you can say all reals except plus or minus 1. Or you can say, in interval notation, you can go from -infinity to -1, union -1 to 1, union 1 to infinity. Okay, so it's like your number line excluding these values, 1 and -1 on your number line. All right, so this is the domain for question number 5. Okay, let's take a look at problem 6. Now, what if we have this function of t, f of t equals 3t divided by the square root of 2 minus t. Now, if we look at our rules, which of them does this function match up with? First, second, or third? Well, this is a combination of 1 and 2. We have a variable in the denominator, and we also have a radical, which contains a radicand that is a variable. So we're looking at case 3, a combination of 1 and 2. Okay, so let's go ahead and write down the approach here. So what we have is a denominator with a radical containing a variable, radicand. All right, so the denominator is a radical with a variable radicand. In that case, you're simply going to set that radicand, that variable radicand, to what? To strictly greater than 0 and solve. All right, that's a combination of steps numbers 1 and 2. So let's go ahead and do that. So you just extract the radicand. Okay, if you don't know what the radicand is that expression that's inside the square root. That, ladies and gentlemen, is your radicand. Okay, so we're going to extract that. 2 minus t, that has to be greater than 0. To get t by itself, subtract both sides by 2. And then you're left with negative t is greater than -2. And then you divide both sides by -1. Okay, and then you get t. Now, what's something you always want to keep in mind whenever you're solving inequalities? You always want to remember that whenever you divide or multiply by negative, you switch the orientation of your inequality symbol. So this becomes t is less than -2 over -1, +2. So t is less than 2, that's your domain, okay? So domain is t is less than 2 using inequality notation. If you want to use interval notation, you're basically going from negative infinity all the way to 2, parentheses to exclude 2, and that's the domain for question number 6. Okay, now let's take a look at problem number 7. Now, what if we have the function f of x equals the third root of 3x minus 5? Okay, so in this case, what do we have? Case 1, 2, or case 3? This kind of looks like case number 2, but let's inspect the index closely, all right? The radicand already has a variable, okay? That's a requirement for case 2, but what about the index? The index has to be even. In this case, the index is odd. So that means this function right here does not match any of the cases in our rules, which means that we do not have any restrictions on the domain. Okay, so let's just put a side note here that the radical, has an odd index. In order for there to be constraints on the inputs, you need to be taking an even power. Okay, that's the only time you end up with imaginary outputs is when you're taking an even root of a negative number. When you're taking an odd root, you never end up with imaginary outputs. Okay, so since the radical has an odd index, that automatically means we have no constraints on the domain. All right, so let's write down our answer. Domain. Domain is, you can write it as big R, or you can say instead of all real numbers, or you can say in interval notation, negative infinity to infinity, like that, okay? Okay, let's take a look at the last one for this review clip. Let's say you have the function f of x equals the square root of 3 minus 4x. All right, now, is this case 1, 2, or 3? We don't have any denominator variable polynomials here, so it cannot be 1, which means it can't be 3 either. We have a radical. What's the index here? Whenever we don't have numbers, you know the default index is 2, right? And 2 is odd. I'm sorry, 2 is even. So 2 is even. Well, that means that we have constraints. We're going to apply case number 2 here. Okay, so let's write down the steps that we're going to be using. So since the radical, we have the radical has an even index and variable radicand. What's the approach? If you have an even index and a variable radicand, you're simply going to set your radicand to greater than or equal to 0. It's only when it's in the denominator that's when it's greater than, okay? When it's in the numerator, it's greater than or equal to 0. So let's go ahead and do that. Remember what the radicand is the expression underneath the square root. So we extract 3 minus 4x, and then we set it to be greater than or equal to 0. All right, let's get x isolated. Subtract 3 from both sides, and that gives us negative 4x is greater than or equal to negative 3. And then we divide both sides by negative 4. All right, and then we have x. Remember what we talked about earlier? What do you do anytime you divide by negative? You reverse the orientation of your inequality, okay? So this becomes less than or equal to minus over minus plus 3 over 4. That's your domain. All right, so let's write that down. Domain is x as less than or equal to 3 over 4 in inequality notation. If you want to write this in interval notation, basically you have negative infinity all the way to 3 over 4. I don't know where that came from. 3 over 4 is less than or equal to, so we use a bracket. Okay, so just use a bracket notation to indicate that the upper boundary is included in your solution region. So this is the domain of the function in number 8. Thanks so much for taking the time to watch this presentation. I really appreciate it. If you found the contents of this tutorial helpful in your study of functions, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions about the contents we covered in this presentation, just place your questions in the comment section below and we'll be more than glad to support you. Do not forget to subscribe to our channel for updates to other cool tutorials such as this. More clips can be found on math.serve.com under the precalc section. Thanks again for watching and have a wonderful day.